in this example, one of the elements is a dependent current source. So I'd like to first use KVL or KCL first, and then I'm going to show you how we can apply KVL as well, and so that we know how to apply this two methods to find branch current and solve for voltages in the circuit. Okay, so I'm gonna paste the circuit down here, and now to apply KCL we have to find, so step one, so we are going to find so find and label essential nodes, right? Essential nodes. Okay, so let's label all essential nodes. So you have this point, I call it A, because we have at least 3 components that are joined at that point, and there I call it G, right? It's another node, another essential node. Okay, I call it G for obvious reason. So when we have, for here we have 2 essential nodes, so the number of current equations is the number of essential node minus 1. So number of essential nodes minus 1. Okay, so those are the number of branch equations that are independent, right? So I need to specify that, right? So number of independent, right? The number of independent, okay, current equations is the number of essential nodes, right? So that means we have 2 minus 1, which is 1 equation to write. Okay, because one node is selected as a reference node. Right? So in general, okay, so when we have n essential node, okay, one of them will be selected as the reference node. Okay, so we end up with n minus 1 current equations, n minus 1 independent current equations, independent current equations. Okay, So now I'm going to paste the network here. Okay, and then now we use this as a reference. So G, right? So we're gonna assume that this is the ground, right? The voltage there is 0 volt. Okay, then we have A, right, which is the other node. So let us write, okay, KCL at node A. So sum of the current coming to the node, right? Sum of current entering node A equals sum of current that leaving node A. Okay, so let's apply that. That gives me I1, which is the current coming to that node, plus I3 equal to I2. Okay, so that is that current equation that we needed. So we have a dependent source in the circuit. Okay, so in step 2, we write a constraint equation. So which is the equation that relates the current to the dependent source here, which is a current source, and to the current I1, right? Because the dependent source current, right? The current dependent source, that dependent source depend on current I1. So we have I3 equal to 30 I1. Okay. Now, so then now that we know that I1 plus I3 equal to I2, we are going to write I1. So what is I1? So let us find I1. Well, let's just write the equation for, let's just write the expression for I1. So let us write the expression for I1, right, in terms of the voltage at node A. Okay, so what do we have? So let's write that branch. So we have, so we have the 6-volt source, and you agree with me that because the elements are in series, they carry the same current, I can swap the location of the voltage source and then the 54k ohm, right? Because they're in series, right? I can rearrange them, and that doesn't change the network. Okay, so I have A here, and I have 6k, and the current source is there. We have 1.8 kilo ohms here, then we have 8-volt source there. Okay, so this is considered as ground, which is 0 volt, and the voltage at this node, the node A, we call it VA. Okay, so this is VA. So the current I1 is flowing this way. So this is 0 volt. So this point is 6 volt. Well, no, that was 5 volt. Sorry. No, this was 5. That was 5. Okay. So there should be 5. Okay. Now, so we have 5 volt here, and we have 1 volt here. So that means this point is 6 volt, right? Because we're increasing in potential. So that means the network, we have 6 volt, right? Because when you have voltage sources in series, we can add them up. So that is 5 plus 1 volt equal to 6 volt. And we have the 54 kilo ohms, and then we have the 6k, and we have the current source, which is 30I1, so 1.8 kilo ohms, and we have 8 volt. Okay, so we know that this is 0 volt. This we call it VA, the voltage up at the node A. So then we have the current I1 here, we have the current I2 here, and then we have the current I3. So now what is, so we know that I3 equal to, we know that I3 equal to 30I1. Now we're looking for the expression for I1. So when we take that 54k ohm, so the voltage here is 6 volt, the voltage here is VA, and the current is flowing that way from left to right. So that means I1 will be equal to 6 minus VA over R, which is 54 kilo ohms. So 54 kilo ohm. Okay, so this implies then the I3 equal to 30 times 6 minus VA over 54 kilo ohms. Okay, so now we're going to find the expression for I2. Okay, so find the expression for I2. Right, so these are the steps. So step 1, we are going to level all the essential nodes and then select one as a reference node. Then we know the number of equations that we're going to write, and then those equations are going to be in terms of the node voltages. Right, so we know I1 in terms of the node voltage, we know I3 in terms of the node voltage, and then what we wanted to find out now is I2. So I2, right? So for the resistor, right, the 6K ohm resistor, we know this is VA. Okay, so for that resistor, we have 6K here, this VA here, this is 0, that's ground, and the current I2 is flowing from top to bottom, I2. Right, so I2 will be where the current originated from, VA minus 0 over 6K. So then we're going to substitute that in our equation, our KCL equation. So now we are going to substitute okay the expressions of I1, I2, and I3 in the KCL equation, right, which is I1 plus I3 equal to I2. That's what we had above. Okay, so we know that I1 is 6 minus VA over 54K plus I3, which is 30, 6 minus VA over 54K kilo ohm, plus that equals to I2, which is VA over 6K. Okay, so that gives me 6 over 54K, right? So I'm trying to solve for VA. VA is the variable, so VA is the unknown. So we need to solve for VA. So 6 over 54K plus 30 times 6 over 54K. So, well, if you agree with me, we could just, because we're dividing by kilo ohms everywhere, we can just simplify the kilo ohm, right? So we have 6 divided by 4 plus 36. 30 times 6 divided by 54, by 6 divided by 54, not by 4. 54 plus 30 times 6 divided by 54. Okay, that is equal to VA times 1 over 54 plus 30 over 54 plus 1 over 6. Okay, so when we calculate VA, right, it's going to give me 4.65 volt. That's VA. Okay, so because I know VA, okay, now that I know VA, so we know the voltage here is 4.65 volt. Okay, so I can calculate the current I1. I1, we know that was 6 minus 4.65 over 54K. Right? The I1 was 6 minus VA over 54K. So 6 minus 4.65 over 54K. Okay, so that will give me 25 microamps. Okay, so and then we find I2. I2, we know that is VA over 6K. So I2 gives me let's calculate that. So will give me 775 so microamps. And I2 I3 now, right, which is 30 I1. Okay, so it's equal to 750 microamps. Okay, so now we know all the current in all the branches. Now the second question was question 2 was to calculate the power supply or absorbed by each element in the circuit. Okay, so let's calculate that. So I'm going to make a small table. I'm going to make a small table. So let me select this and move it to the side slightly. Okay, so then I'm going to make a table. Okay, now where I'm going to list all the elements. I'm going to list all the elements. So here we have element. So the first one will be the 5-volt source. The second one will be the 54 kilo ohm resistor. The next one will be the 1 ohm source. I can draw this correctly. So one volt source rather, sorry, and we have why is it not giving me a straight line? So then we have the 6 kilo ohm resistor. We have the dependent source. Okay, and then next we have the 1.8 kilo ohm, and then the very last one, we have the 8 volt source. Okay, so now we know the current in each branch, so let's put current here. Okay, so the current I1, which is through the making the same mistake, that's 5, the 5 volt source, I1 will be equal to 25 micro. Okay, so let's say the current is in microamps. Okay, so this will be 25 because they're in series, 25 here as well. The 6K will be we have 775. This the dependent source 750. The 1 kilo ohm 750 micro, and the 8 ohm a volt source is 750 microamps. Now it's fine. Let's find the I don't even know why the line is not giving me. Okay, that's good enough. So we have voltage, that will be in volt. So we have 5 volt here, and the voltage here, which is 54K times I1. Okay, so that gives me 1. Right, so 54K times I1, that gives me 1.35 volt. Okay, so the voltage source is 1 volt, and the 6K, so it's 6 kilo ohm times I2, so that gives me 4.65 volt. Okay, for the dependent source. Now, how do we find the voltage across the dependent source? Let's do that. Okay, so let us find the voltage across the dependent source. So I'm gonna label the voltage plus or minus, let's call this V0. So to find our voltage, I am going to write KVL right around this loop. Okay, so starting from the top, I have V0, okay, plus the voltage across the 1.8. So let me put the current I3 right there, I3. So the voltage here, which is V 1.8, so plus V 1.8K, okay, then plus 8 volt, okay, and then the voltage across the 6K, okay, I'll call it V 6K, so minus V 6K, then that will be equal to 0. Okay, so then I can find V0. So V0 will be minus 8 minus V 1.8K plus V 6K, and I know minus 8, so V 1.8, I can calculate that, which is so let's look. We have 1.8, so we have I3 that's flowing like this way, and then we have 1.8, so let's call this V 1.8K. So I mean, when we use the passing sign convention, V 1.8K will be equal to negative I3, which is negative 1.8 times the current to that, which is 750 microamps. So the voltage will be, and we calculate that, will be minus 1.35 volt. So then it'll be plus 1.35. Let me move this slightly to the right. Okay, and then plus V6K. V6K was equal to 4.65. So it's minus 8 plus 4.65 plus 1.35. So that is negative 2. So negative 8 plus 6 equal to negative 2 volt. So the voltage across the dependent source, it will be negative 2 volt. The voltage across the as level, right? So if you have flipped the polarity, then it'll be, so it's minus, if you like, 1.35, right, as our level on the figure here, and this will be a volt. Now let's calculate power. So now we are going to calculate power. We're going to write the equations down. Okay, so let's calculate power. Okay, equation. So I'm going to write the equation here. So for the 5 volt source, the current is flowing from minus to plus, so it's minus 5 times I1. Okay, and that is minus 1.125. All right, so power here in microwatt minus 125. So the 54 kilo ohm, right? We get the power through a resistor is Ri square. So that would be 33.75 microwatt. The power through the 1 ohm resistor will be the current from minus to plus, so minus 1 times I1, right? So that gives me negative 25 microwatt, right? Because the current is minus 5 microamps. For the 6K, it's also Ri square. And when we follow the passive sign convention, if we use the voltage, we're going to get the same thing. So for that, the 6K, we have 3603.75 microwatt. For the dependent source, the current is flowing from minus to plus. So we have the voltage across the dependent source, which is the current is flowing from minus to plus, so minus, right, Vi. So so the voltage minus Vi, so that will be minus 2 times the current, which is 30 I1. So the current there is 750 micro. So that will give me a positive number, 1500 microwatt. And then for 1.8 kilo ohms, so we still have Ri square. So that gives me then 12.5. And then the last one, the current I3 is flowing from minus to plus, so minus 8 times I3. So that gives me negative 6,000 microwatt. Okay, so now the power supply and the power absorbed. So let me circle the power that I supply. So this is supply, this is supplied because it's negative, this is supply. Okay, so those are power supply. So there's supplied, okay, and the rest are positive, so those are the power absorbed, right? So there's absorbed power, okay, so this absorb power, okay, so this is absorb, and this absorb. Okay, so when we add all the supply power and the absorb power, we should get 0, right? So the sum of supplied power okay, so let me see, absorb power equal to the sum of supplied power. Okay. All right. So that is when we use the KCL method, right? So that's the end of method 1. Method 1, which is KCL. So method 2, we are going to use KVL. Okay. So what are the steps? Right. So step 1. So find and label essential branches. And step 2. Okay. So find the number of independent voltage equations okay. And step 2 and step 3, now we're going to label the voltage across each component. Okay. And then in step 4, I will write the loop equations. Okay, so this is the network that we were dealing with. Okay, so from the previous, from what we did previously, we have 2 essential nodes. Okay, so step 1, we find 2 essential nodes. So here we have 2 essential nodes. Right, so the essential nodes are where we have more, so where 2, 3 or more, 3 or more element are joined. Okay, so now so essential branches connect the essential node. Okay, so so we have 3 here. So we have 3 essential branches. So that carries I1, I2, and I3 as label here. Now, so what we need to do next, step 2, right? Find the number of voltage equation. Step 2. So number of independent voltage equation of independent voltage equations. Okay, so the number of independent voltage equation is equal to the number of branches minus the number of essential node minus 1. So that's 3 minus 2 minus 1. That's 3 minus 1, which is 2. So we have 2 independent voltage equations. So for that, we are going to label okay. So now I'm going to call this V1, I'm going to call this V2, right, if you like. I'm going to call this V3, and I'm going to call this V0. Right, it doesn't matter. I could call this V0. So now we label the voltages across each component. So what are the loops? So I'll call this loop 1. Okay, so loop A, and I'll call this loop B. Well, if you want, I could call it loop 1 and loop 2. Okay, so loop 1 will have IA, and loop 2 will have IB. Okay, so because we need 2 independent voltage equations. So now I'm gonna write the loop 1 equation. Loop 1 equation. So starting from the node G, so moving this way, then I come across the -5 volt. The negative polarity of the voltage source, the 5 voltage source, so -5. Now plus V1 minus 1 plus V2, that is equal to 0. Okay, so we reach, that's the loop equation 1. Okay, but what is V1? V1 is 54K I1, that's Ohm's law. V2 is 6K times I2. Okay, but when you look at the 6K ohm, we label the polarity as this. So the current IA is flowing down, and the current IB, so let me use a different color. The current IA is flowing downward, IA, and the current IB for this loop equation is flowing upward. So when I use the passive sign convention, this will be, so I2, right? I2, which is this current, equals to IA minus IB. So that means when we substitute that in there, okay, 6K IA minus IB. Right, remember, so because the equations, like the voltage equations, are going to be in terms of the loop current, so that's IA and IB. So that's why I'm trying to substitute that in there. So V1, which is 54K I1 plus V2, which is 6K. So IA equal to I1, right? So we know that IA equal to I1. So IA minus IB, that's equal to 6. So that's my first equation. Now, loop 2 equation. Okay, so starting from node A and moving clockwise, we have V0 minus V3 plus 8 minus V2 equal to 0. So what is V3? We know V2 already. So V3 is equal to 1.8 times I3. Okay, so but I3 equal to minus IB. So V3 is minus 1.8 kilo ohm. So IB. So we have V0. So minus V3, that becomes plus 1.8 kilo ohm IB minus V2, which is 6 kilo ohm IA minus IB. Now plus 8 equal to 0. So that's my equation number 2. Now, That's equation number 2. So as you can see, we have two equations, 3 unknown, right? V0, we don't know V0. So we have IA, IB, and V0 as unknown. Okay, so because we have a dependent source, we need to find, right? So because there is a dependent source in the network, a dependent in the circuit, we need to find the constraint equation. Okay, so that means the relationship between the dependent current source and the current that it depends on. So we know that the current is 30 I1. The current of the dependent source is 30 I1. Okay, so and then we know that 30 I1, and then we know that, right, this is I3 equal to 30 I1, right? I3 equal to 30 I1. So bet I1 equal to IA, right? So that means I3, which is 30 IA, but I3, we know that is equal to negative IB. So that means IB plus 30, well, IB, if you like, IB equal to negative 30 IA. Okay, so we know this as well. So if I take the first equation and this equation, the constraint equation, okay, I should be able to find IA and IB, right? Because we only have two variables on those two equations, right? So I'm gonna make this equation, which is 54K IA now plus 6 IA minus IB, that is equal to 6, and then IB plus 30 IA equal to 0. Okay, well, I could just substitute that in that equation if you like. So that may have 54K IA plus 6K, which is IA plus 30 IA equal to 6. So that gives me IA, which is 6 divided by 54K plus 6K times 30. So IA will be equal to 25 microamps. Okay, so then I can find IB, which is minus 30 times 25 microamps. Okay, which is negative 750 microamps IB. So that implies that I3 equal to 750 microamps. So we know this is equal to I1 okay. So then we can use equation number 2 to find V0. Okay. So if we calculate V0, right, so we wrote the equations, we wrote the node equation, the mesh equations, or the loop equations, and we found all the current. Okay. Now, so we can find the current through the current I2. Right. So if I add node A, okay, so we know IA and IB, so that the KVL method let us find IA and IB, so we can use those to find the branch current. So we know that I2 is IA, okay, so I2 we had it here, right? I2, so we had it over here, right? I2 equal to IA minus IB. Okay, so we know that I2 equal to IA minus IB. So that gives me 25 microamps minus 750 microamps equal to 775 microamps. That's I2. So as you can see, we are able to find all the branch current. Okay, so we use the node method, the KVL method, to find all the branch current, and then using the branch current we can calculate the power as we did when we did the KVL. So with the node, we know that this is 25 microamps, this is 775 microamps, this is 750 microamps. So we know all the branch current, we can use all the branch current that we just calculated to calculate the power absorbed or supplied by each component. All right, thank you. So please click on the like button, like my videos, please, and please subscribe as well.